Oh, okay, we're gonna get started in about 4 minutes. Where's everybody else? Are they rushing through the snow and the ice? Maybe they're on time. Probably, but we have a stick. We have a stick. Hello. I'm doing this one. They're not usual. All right. Good afternoon, kind people. How are we doing today on Springer? Oh, I'm back. I'm showing my age again. You guys ever watch Jerry Springer? Oh, that's how I always started, right? Today on Springer. No? Oh, my bad. All right. So probability distributions right here. There are two key facts about probability distributions. The first is that each probability that's assigned must make sense, i.e. a probability cannot be negative and it cannot be greater than 1. Yes? So for example, in this first example, we see right here, see a negative 0.3 probability. That does not make sense. I cannot have a negative 30% chance of something happening. It's between 0 and 1, between 0 and 100%. The second thing right here is that for it to be a probability distribution, the sum of all the probabilities, i.e. when you add them all together, the answer must be 1. I.e., the probability distribution must be complete. It must take into account all possibilities. All right. Questions there. So to be a distribution, if you add up all the probabilities, if they're not one, then it is not a probability distribution. And then we worked with an example or two using the distributions. The first thing is we assume that all of the events are mutually exclusive, or the mutual exclusivity has already been accounted for. And so if I ask what's the probability that 3 people will have high blood pressure, then the answer is simply going to be 0.8. If I ask what's the probability of 2 or 3, we simply need to add them together, right? If we said 2 and 3, that would be impossible, yes? Yes? On the other hand, if I said the first week 2 people had high blood pressure, and then the following week we went back to a different place and we checked again, and then 3 people, that would be different. We could figure that out by just multiplying them together, because and would mean to multiply. Yes. And then of course the last example we did was the at least one. We showed you 2 ways of working out the at least one probability. The first way is to simply add them up. 0.41 plus 0.27 plus 0.08 plus 0.01. That at least one means one or more. So if you just add all of these up, this gives the answer. Or you can just subtract out what was missing. The whole thing is 1, correct? So if I subtract out the 0, what will be left is all of these things added together. The reason why they prefer using the subtraction sign right here is that sometimes this can be huge. Imagine if there were 50 possibilities, right? 50 people come into the place. Yes? What's the probability of at least one of them has high blood pressure? You don't go add them 49, 50 numbers, right? Much better just go 1 minus the probability of none of them, and then that's it. All right? Questions? There are actually some cases where this can actually be an infinite number of numbers. But even though it's infinite, you can still calculate it, because you just go 1 minus none, and that still gives you the answer. All right. No more mind blowing for today. Questions there? That's where we stop. Questions there? Yes, you can add up an infinite number of numbers and get an answer. You can. All right. I digress. And so that takes us to the average of a random variable. The average of a random variable is calculated by multiplying each score by its probability and then adding all those numbers up. This is how you write it in mathematics, which actually makes no sense at all. But literally saying, take the score, multiply by its probability, do this for each one, and then add all the answers up. When you do this right here, you get a weighted average, and that weighted average will be the mean. Questions there before we try an example or 55. Again, the expected value right here, instead of calling the average, because we're looking at random variables, they call it the expected value. Because the idea of a random is we can't actually predict what will happen next. Yes? So the expected value right here is saying all else being even, this is what we expect to happen. I.e., this is the average outcome. Yes? So instead of they calling the average, they call it the expected value. Okay, again, it's going to be the central point. It's the mean. And this is our lovely formula for calculating the mean. So now, from this point on in the class, a lot of these questions take forever to read. So I do apologize in advance for having to read them all out. But I do. A computer monitor is comprised or composed of a very large number of points of light called pixels. It is not uncommon for a few of these pixels to be defective. Let X represent the number of defective pixels on a randomly chosen monitor. The probability distribution for X is 0 pixels, 20%. 1 pixel, 0.5 or 50%. 2 pixels gone out, 0.2, and 3 pixels gone out, 10% or 0.1. So the question is, can you compute the mean number or the average number of defective pixels? All right. The first thing that I want you to note is It's not just going to be the average of 1, 2, 3, and 5. The average of 1, 2, 3, that's divided by 4. 3 plus 2 is 5. 5 plus 1 is 6. 6 divided by 4 is 1.5, right? The average is not going to be 1.5 because 1 is a lot more likely to happen. Yes? Right? If, for example, you had an 80% of 0 pixels being out, the average is not going to be 1.5, right? Right? And so that's why we're not just adding these 4 numbers up and dividing by 4. In other words, instead, what we're going to do is we're going to weight each outcome. And what that means for us is we are going to go column-wise. You're going to multiply these together. What is 0 times 0.2? 0. Plus, what is 1 times 0.5? 0.5. What is 2 times 0.2? 2 times 0.2. That's going to be 0.4, I believe. And what's 3 times 0.1? 3 times 0.1. That is 0.3. And you add those 4 numbers up. 0 plus 0.5 is 0.5. 0.5 plus 4 is 0.9. 0.9 plus 3 is 1.2. This is going to be the average number of pixels that's going to be out if you select a screen. So in other words, on average, the expected is that it'll have about 1 pixel being out. Yeah, but you know, that's really annoying, right? When you look at the screen and there's that 1 pixel that's not working, and you can tell, and you keep looking at it over and over and over again. Yes, right? But it's going to be about 1 pixel that's defective. Questions there? And so that's what they have for us right here. The mean is multiply each one by its probability, add them up, and get an answer of 1.2. Questions there? That is correct. That's correct. Because the mean in this example, for example, is the average number of broken pixels, right? So it's an average. How many broken pixels we have an average? Could be anything. So let's say the numbers was 1, 10 pixels broken, 20 pixels broken, and 30 pixels broken, right? The average is going to be 12. Yeah. So no, it's not like a probability. It can be anything. It's an actual average, right? So for example, if I said, hey, the average score on test 1 was 80, the average test score or whatever on test 2, it's a real average. That's what it is. Anybody else? All right. That takes us to the standard deviation. You guys remember what the standard deviation is? Anybody? Don't you all raise your hand at the same time? Anybody? Somebody faked me out of back there. Go ahead and say it. I'll correct it if it's not. It is the average spread away from the mean, or the average distance away from the mean. Yes, ma'am, that is correct. So you put the mean in, it'll be in the center, right? You have some points above it and some points below it. It'll be the average distance away from the mean above and below. All right. So you get an idea how spread out. If the standard deviation is small, all numbers are really close to the mean. Standard deviation is large, the numbers are really far away from the mean. All right. All right, so how we calculate the standard deviation? Very carefully. So, if you recall, your standard deviation is the squared variance, yes? The squared deviations, yes? And so what you have right here is you have x minus mu. That gives me my deviation. You raise that to the second power. That gives me my squared deviations. And then you multiply that by the probability. Add all those up. And then take the square root. And that gives us the standard deviation. If we do not take the square root, it'll give us the variance. Questions there? Comments, queries, concerns? All right, so let's work through the an example. This example is slightly different from the one that I have. Let's start here. Go ahead and see if you can verify the expected value in this new example that I have right here. So let me remove this line for now. We'll put it back in a second. This is a regular table. So again, this right here is your pixels are going out. But note that I changed the probabilities. It's different from the question we just did. Go ahead and find the expected value. Use the formula we just learned. Find the expected value, because that's always your first step when you're finding the standard deviation, is you need the mean first. Go ahead and find the expected value. Oh, any questions? I'm wanting you like me? One that's like one. Oh, you didn't go there? Yeah, so great. I wish I was just, back in the day. I wish I was just. Just staying up all night doing schoolwork. So it's just right. That's exactly right. All right, everyone's with me? Or anyone with a question? No. Yeah, we're just doing the mean right now. We'll do the standard deviation together. Right now, we're just doing the mean. So what happens right here is multiply each square by with and add it to the further. The answer is up there. I just want us to verify it. Make sure we feel like that's down for you. All right, can I step off? The answer is 1, correct? Y'all got an answer of 1? Expected value, yes? So you know that's fine. I can work around it. It's not up there, it's not on the board. All right, cool. So now, once you have this expected value, you have to do a new table. And that new table right here is you need to find the squared values. So 0 squared is 1 squared is 2 squared is, and 3 squared is 9. And then what you do is you do the same process you just did, except you're using this row. So you go probability times 0, probability times 1, probability times 4, probability times 9, and you add them up. Go ahead, multiply each of these right here and add them up. We're doing this part right here of the formula. So go ahead and multiply each one of them right here and add them up. We're doing this part of the formula right here. When we did that, our answer, what did I just do? When we did that right here, our answer should be 1.8. When we multiply this, our answer should be 1.8. Then we need to subtract the mean squared, but the mean squared is still 1, correct? Right? Yes? Subtract 1, that gives us 0.8, and that completes this piece right here. 0.8 is your variance. This right here is your variance, sigma squared. And once you have the variance, you just take the square root, and that gives us our standard deviation. Our standard deviation is 0.894. Question? Questions? All right. So we have an example for you guys to work. Where is my pencil? I need it. All right. Uh, so I have this example right here. This right here is people coming into a burger store. This right here is the distribution for the number of burgers they will buy. There is a 30% chance they won't buy a burger, i.e. they'll get some fish or something else. There is a 40% chance that they will buy one burger. And then there is a 30% chance that they will buy two burgers. Question, is this a probability distribution? Is this the probability distribution? Is each assigned probability between 0 and 1? If I add up all the probabilities, do they add up to exactly 1? Then it is a probability distribution. What I want you to do now is to find the mean and the standard deviation for this probability distribution. So I want you to do the whole thing now. By hand. Anyone needs an assist? I'm fine. I'm fine. I'm fine. It's brown. And yay. So what we're doing here is finding the mean. Find the mean is you multiply these four by probability. Okay. So that's not. So what's what that's it. All right, guys, let's go ahead and let's see if we got the correct answer. Should have been the square root of 0.6 for the last piece. All right, so the first step right here, excuse me, the first step right here is they want us to find the mean or the expected value. Remember, both of these things are the same name, right? I could also call it the average, yes? And so to find the expected value, as I have to take each of these, 0.3 multiplied by 0.4 multiplied by 1, and then 0.3 multiplied by 2, and add all those numbers up, and that'll give me my expected number of burgers people will eat, yeah? So let me put that back up here for us. And so you see right here, 0 times 0.3, 1 times 0.4, 2 times 0.3, and you add those up, you get an answer of 1. And so the average is going to be 1. Yes? The next thing we do is we extend the table. And so we're adding these points right here, 0, 1, and 4. How did I get 0, 1, and 4? See, I have to take this and I have to raise it to the second power. Yes? 0 squared is 0, 1 squared is 1, 2 squared is 4. All right? And then I do a similar process, except I use these two rows instead. So I go 0 times 0.3, 1 times 0.4, and then 4 times 0.3. And I add all those up. And that gives me an answer of 0.6. To get the variance, I have to take this score and subtract the mean squared. So 0.6 minus 1 squared gives me an answer of 0.6, and that's my variance. And to get the standard deviation, the last step is to then take the square root. Square root of 0.6 is 0.07745. I didn't see how many decimal places, so whatever you had is fine. And that gives me my standard deviation. Question. Comments, queries, or concerns? All right, so can I step out? Anyone still writing? Okay, cool. Well, hope you guys got great plans for this weekend. Yes.
The test still next Friday?
Yes. Literally, we'll hope to get to like halfway 5.2 today, and then we'll almost finish 5.3 on Monday. Yeah, so we should be good. If not, I'll push back to next week Monday. But we should be good to get there. Yeah, it's a really short section. Only three items on the test: 5.1, 5.2, and 5.3. That's all. That's on the next step. All right, so can I step on? Someone said, I'm waiting for all the other people who are writing, not just one. All right, yes, we're good. No as in go back a slide, or no as in just wait?
Yes.
Oh, question, go ahead.
You lost me.
Okay, so do you remember how we got these numbers right here? We were multiplying, we're going down the column. Yes? Yes? We're doing the same thing, but we're just using the squared numbers instead. So this times this times this, and this times this, and we're adding them up together. So x squared means this row, p of x means this row. So these are the ones we're multiplying together. All right? Yes or no? Maybe so. You want me to check your answer? Check your work. Give me 1 second. Give me 1 second. All right. Anybody else? I'll come back. All right, so this is the example that their own example. We did several already. All right, and so that ends this right here. There's one more example in 5.1. There are many occasions when we want to predict how much we are likely to gain or to lose. This right here, again, is still called your expected value. If your expected value is positive, it means you're gaining. And if it is negative, it means you are losing. Okay? Now, anyone ever heard of a casino? Ever heard of a casino? Every single game at a casino has an expected value that is negative for the player. For every single game at a casino, your expected value is negative. So what does that mean? Once you start playing, on average, you will lose money. That's why when you go to a casino, you're going to have fun, not to make money. Literally every single game is designed so that you will lose. A fair game is a game where the expected value is 0, i.e., you're expected to win as much as you lose. In that situation, that's considered to be a fair game. Now, if you walk into the same casino and you're the casino owner, the expected value is positive, yes? Because from your point of view, the game is designed for you, the house, to win, yes? And so for you, the expected value is positive. And so literally, the more people play, the more money you will make. Yes? That's why there are lots of rules that govern the creation and the running of casinos. Because literally you can just change the game, just jack up the prices and just cash money 24/7. Right? And so but that's why there are lots of rules, because what happened is that if they want those rules, they can claim it's one game, but they change the game around. So for example, if you're playing 21 and they remove 2 of the jacks from the deck, you have a smaller chance of getting a 21, right? Right? And so you're more likely to lose. They can do these kind of things to adjust the probabilities in their favor. And that's why there are lots of rules on governing how you run these establishments to try and prevent that from happening. But anyways, for a fundraiser, oh, I should hit this. Again, like I said, these things will take forever to read. For a fundraiser, a club is selling fortune cookies at a price of $1 per cookie. Each cookie contains a piece of paper with a different number written on it. A random drawing will determine which number is the winner of a dinner for 2 at a local restaurant. The dinner is valued at $45. Since the fortune cookies were donated to the club, we can ignore the cost of the cookies. The club sold 587 cookies before the drawing. Our friend Deja bought 15 cookies. What is the probability that she will win the dinner for 2? 15 out of 587 is the correct answer. The probability that she wins the dinner for 2 is 15 out of 587. Question, therefore, what's the probability that she does not win the dinner for 2? One minus this number, yes? So the probability of winning the dinner for 2 is 0.026. Therefore, the probability of her not winning the dinner for 2 is going to be 0.974. Questions so far? This is not a good game, yeah? Not a good game. We can push things a little further. What is the expected earnings rounded to the two decimal places? If she wins, she gets a $45 voucher to a table or to a dinner. If she does not win, she gets nothing, right? So her expected value will be to multiply these things together, and then add the answers. Yes? And so her expected value right here, they decide to round to four decimal places to make the numbers work out a little bit better. You multiply this times this times this, add them up, and you get $1.15. Her expected value for this right here is $1.15. Questions there? How much did she effectively contribute to the club? Statistically speaking, she bought 15 cookies at $1 each for a total of $15. Yes? But she is expected to get back $1.15. So she is effectively contributing $13.85 to the to the group, to the club. Questions there? Let's go over that in a little bit of detail right here. Let's make this 3%. Let's say she has a 3% chance of winning. That means if they held this raffle for like 100 times, so let's say this is their main money, so they held like every 3 weeks or so, they have this raffle right here. Out of 100 raffles, she will win about three of those 100 raffles. Yes? 3%. She'll win about three of those raffles. Yes? And so that's going to mean $45, $45, and $45 that she will get three times. Yes? But the other 97 times, she will get nothing. And so in the other 97 times, she would give them $15. Yes? Well, actually, all 100 times, she give them $15. Yes? And so what this is saying right here is that if I did this 100 times, the club will get, move this one place twice, $1,385, and she would get $45 back three times. Does that make sense? And so that will account for the total of the $1,500 that she spent over the 100 raffles that she participated in. All right. And so that's why they're saying her effective contribution is this amount. Because what happens is that every once in a while the club will pay her $45 for her to go to dinner. All right. Questions there? All right, cool. All right, so that takes us into 5.2, the binomial distribution. Dum dum dum. All right, the binomial distribution. Anybody out there love to play some basketball? Basketball? No? You ever heard of this guy, Stephen Curry? No, you never heard of this guy, Stephen Curry? You know Stephen Curry's taller than me, right? When you watch him on my small screen, he looks so small. But you know he's taller than me, right? He's 6'3". Yeah, he's taller than me. It's weird, right? You look at him, he's smaller than everybody else. So, but no, he's actually. I digress. Mr. Stephen Curry has about, let's round the numbers out, about a 90% chance of making a free throw. You guys know what a free throw is? Right? So he's the act of shooting a three ball and he gets fouled. And so he goes to the line. How many times is he going to shoot those three throws? He's going to shoot him three times. Okay, it's a three ball. Right? So he gets to shoot him three times. Yeah? Right? The probability that he makes each one is going to be the same, 90%. Yeah? Yeah. That special scenario where you have something that's happening over and over and over again, where nothing in the situation is changing and the probability is not changing, goes by the name what's called a binomial process or a binomial distribution. Let me go ahead and identify the pieces for you, like so. A binomial distribution is made up of four key qualities. The first is that there is a fixed number of trials or a fixed number of events. before Mr. Stephen Curry steps to the line, we know how many times he's going to shoot the ball. Yes? That's going to be 3 times. Yes? For binomial distribution, it's always a fixed number of trials. We know how many times whatever is going to happen is about to happen. The second thing right here is that the trials are independent and identical. Independent mean whether or not he makes the basket, that has no effect on the next time he's going to shoot the ball. Yes, he's a professional. He shot what, 50,000 free throws in his life. If he makes one, that don't affect him. If he doesn't make it, that doesn't affect him. It's the same shot every single time. Yeah. So it's independent. Whether or not he makes one or not doesn't affect the next shot. And it's identical. It's the same basket. It's the same ball. It's the same distance from the line. It's the same amount of time he has to shoot the ball. Yes? This right here is called IDD. Independent and identical. Right? The third thing about your binomial distribution is that there are only 2 possible outcomes. When he shoots the free throw, either it goes in the basket or he misses. Yes? The 2 outcomes, one of them is labeled as a success, the other one is labeled as a failure. So he makes the basket, that's a success, and of course, you're not on his team. And if he doesn't make the basket, then that's a failure. Yes? Yes? So fixed number of trials. Before we start, we know how many times it's going to happen. IDD, independent and identical. And then there are 2 outcomes, success or failure. And then the last one right here is that the probabilities don't change. The probability of a success is fixed. We call it lowercase p. The probability of a failure is also fixed. It's going to be 1 minus p. Uh-oh. Uh-oh. I have to write that myself. The probability of a failure, so the probability of a success is labeled as p. The probability of a failure is labeled as q, which is going to be 1 minus p. Because there are only 2 outcomes, right? If I have an 80% of making the basket, then I have a 20% not making the basket. Yes? What sets the binomial distribution apart is that there are only 2 outcomes. That's why it's called binomial, because 2 possibilities. All right? If I know the probability of the success, I know the probability of the failure. Questions there? Comments, queries, concerns? Let's take this for a ride. First things first is we determine our variable. X is your binomial discrete random variable. R is the number of successes for a given experiment. And N is the number of trials. And P is the probability of success. And Q is the probability of a failure. Now let me write this down for us right here. We write this right here. Say for example, X is the number of baskets made. Number of made baskets. Then we write this right here. X follows a binomial distribution BIN, N comma P. X follows a binomial distribution where there are 3 shots because he got fouled shooting a 3 ball, and P is going to be 0.9. He has a 90% chance. He has a 90% chance of making any one of those 3 baskets. Okay. Implied, when you see this thing like right here, implied right here is that the 4 conditions are being met. That little X follows a binomial distribution. It means those 4 things are met. All right. Guys, remember what the 4 things are? Remind me. Fixed number of trials, IDD, identical and independent trials. 2 more. There are only 2 outcomes, a success or a failure. And then the last one is the probability of a success is fixed. It's always 90%. Yes? And then I can write this right here, the probability of X equals R. So this is the probability that the number of made baskets is R. In real life, you'll see this right here. What's the probability that he makes all three? The probability that the number of made baskets is equals to 3. And then we will show you how to calculate this probability in a second. Right? But literally, this reads, find the probability that the number of made baskets is 3. Or find the probability that the number of made baskets is 0. Questions there?
Can you go back to what each of those things were again?
I'm going to delete this. So take a picture first. You got that? All right. So R is the number of successes. N is the number of trials. P is the probability of a success. Q is the probability of a failure. Q is equal to 1 minus P. I think it's written on here. Q equals 1 minus P. It'll write up in a second. There it is. Is that the time? All right. Questions? Don't you hate when time just flies like this? It's just going. Questions? All right, cool. All right. Decide if this is a binomial or not. It is or it is not. A fair coin is tossed 10 times. Is this a binomial distribution? You have to check the 4 things. 1, is it a fixed number of trials? 10 of them, right? Is it IDD, independent and identical? It is. Is the only 2 outcomes? Is either a success you get a head, or a failure you don't get heads. Yes? And is the probability fixed? Is it always the same probability to get heads? And so therefore it is binomial. All right. Let's try again. 5 basketball players are going to attempt 1 free throw. Is this a binomial distribution? I have 1 person saying no. Is this a binomial distribution? Or a binomial experiment, to be more precise? It is not. Let's go. 1, do we have a fixed number of trials? Yes, there will be 5 baskets shot. We know that already, yeah? 2, I said IDD. Are the events identical and independent? They're not, because it's 5 different players, yeah? If Steph Curry is shooting the first and I'm shooting the second, it is not the same outcome, yes? Yes? Right? And that's what blows the whole thing up. But also the probabilities are going to be different, yes? The probability of him making is 90, probability of me making is 20. Right? And so yeah, it's not a binomial distribution. But there were only 2 outcomes, yes? Either a probability, either a success, they made baskets, failure, not made basket, but that's not good enough. All right, there are 10 cards in the box. 5 are red, 5 are green. 3 cards are drawn at random. Is this a binomial distribution? X is the number of red cards drawn. Is this a binomial distribution? 1, do we have a fixed number of trials? 3 cards are going to get drawn, yes? Are the trials IDD, identical and independent? Yes, they are, because every single time we're doing exactly the same thing. I'm drawing 3 cards. I got 10, pulling 3 of them, yeah? What's number 3 again? Oh, are there 2 outcomes? 2 possible outcomes. Let me select a card. The card is either going to be red or green. Last, is the probability fixed? The probability fixed. Probability of getting a red card. Is it fixed? It is not. Right? The first time I pull a card, it's green. The next time I pull a card, the probability of a red card is going to change. Initially, it was 5 out of 10, yes? The second time is going to be 5 out of 9. The first card is green, yes? And so it is not a binomial distribution. Probabilities aren't fixed. Questions there? Yeah, again, it is not because the trials are not independent. Probability is not fixed. All right, I have time to this one right here. I do. John damaged his credit card. There is an 80% chance that a transaction will be successful. John is going to use his credit card 8 times today. X is the probability of a successful swipe. Therefore, X follows a binomial distribution with N being 8. There are going to be 8 trials, and the probability of a success is going to be 0.8. The question is, what's the probability that 6 out of his 8 attempts will be successful? Let's go ahead and get an answer to this question right here. To get an answer to this question right here, we have to use this thing called SALT. You guys ever heard of SALT? So if you go onto your where's my Chrome browser? It works better in Chrome. And you Google, where's my button? And you Google SALT, WebAssign. It's the one that you used on the test. Whatever it is, WebAssign SALT. It will pull up this lovely thing right here, SALT. But this time, we're going to distribution calculators. We're moving on up to the east side, to a deluxe apartment in the sky. I really am showing my age, aren't I? We go on to the distribution calculators right here, and over here we select the distribution. The one we want is the binomial distribution. That's the one we want. That's the one we're studying in chapter 5. Right here, a binomial distribution needs 2 numbers, right? N and P, yeah? They remind us by putting N up here and P up here for the 2. N was 8, I believe. There he was swiping his card 8 times, and the probability of a success was 60%. Yeah? Yeah? Oh, my bad. Oh, his card is not that damaged. Probability of success is 80%. So right here. And so then over here, you see this lovely picture being drawn for you right here. The probability that 2 are successful is this. The probability that 3 are successful. If you click on each one, it'll give you the probability. The question asks for 6, correct? So if I just tap right here, see 0.2936. Can you see that right here? It's 6, 0.2936. That's the probability that 6 of them. Didn't go 2.0. That's how I got this answer right here. 0.2936. All right. Salt will do it for you. Let me show you a different way to get to the same answer. If you click up here and you click on equals, see I have these choices right here. If I click on equal, this symbol right here will change to an equal sign. So I click on equal. So now they're asking the probability x equals, and I can type in 6 into this box. And then you get the answer again, 2.936. The probability that it will work exactly 6 times is going to be 2.936. Question? Comments? If I wanted to know 7 times, I'll just change this to a 7. There's a 33% chance that it will work 7 times. Questions there? All right, we're going to have to stop here. Oh, I ran out of time, y'all. I'm so sad. I didn't want to. All right, let's